In this online lecture, we are going to learn about enthalpy change and Hess law. Now imagine you and some friends are hiking up a mountain trail. You come to a fork in the trail and decide to break into two groups. One group follows a short, steep path, while the other one takes a set of stairs with gradual slope. Eventually, both groups will reach the top of the trail and will see the same view. Although the two groups took different routes, everyone reached the same place. We can think of something like this for chemical reactions as well. So they behave in a similar way as these mountain climbers. There is more than one possible route to get from reactants to products. Now let us see how. From experimental evidence, chemists have found that change in enthalpy in a chemical process is independent of the path taken. So, what do we mean by that? So, now let's go ahead and try to look into this thing. So, for example, I have a reaction N2 plus O2 becomes 2NO2. For the balancing purposes, let's put 2 in front of here. Okay. So delta H for this one step reaction is 68 kilojoule. Okay. Now let us say we are producing nitrogen dioxide by two-step process. Let's see how. So you react nitrogen with oxygen and it becomes 2NO. Okay, this is a two-step process which involves the formation of nitrogen dioxide. This is a one-step method to form the nitrogen dioxide. So this one is, so I will write this is one-step process and this one is two-step. Just wait. Two-step process. Now what's the second step? So you produce 2NO here. So this 2NO will go ahead and react again with oxygen gas to form 2NO2 gas, right? So the delta H for this step is 180 kilojoules and the delta H for this step is minus 112 kilojoules. Now, if you add these two equations, you get the equation for the overall reaction. So let's go ahead and add these two equations here. So you can see you have 2NO on this side and 2NO on this side. This is right hand side, this is left hand side. So you can go ahead and cancel them just like you do in the mathematical equation. Let's say you have x plus y is equal to 2z and then let's say 2z plus x is equal to y. Then you can get rid of this, okay? And then you can get rid of this. So they behave like the same mathematical equation. So you can get rid of these. Now, if you go ahead and add them to get the overall reaction, so you have nitrogen plus 2 oxygen gives you 2NO2, right? Which is same as this, right? So here you took two steps to make the nitrogen dioxide gas. Here you took one step method to make nitrogen dioxide gas. Now, if the similar thing will be valid for the delta H values as well, since we added these equations, we have to add delta H value as well. So 180 minus 112 should give you 68 kilojoules. So, which is the same. So what we'll be saying is that the delta H, the enthalpy change involved in a chemical process is independent of the path taken. So whether you go this way or whether you go this way, like those mountain climbers, whether you take the steep slope or you take the gradual slope, you will both be rewarded with the same thing. Okay, so this is one thing. So this means that in going from an initial set of reactants to a final set of products, the change in enthalpy is the same, regardless of whether the conversion happens in one step or it takes place in series of steps. Okay, so there was a scientist, there was a professor at the University of St. Petersburg, Russia, whose name was Henry Hess. So he was interested in whether the number of steps involved in a chemical process affects the enthalpy change of a reaction. At time when most chemists were identifying new chemical substances, he was interested in why some atoms are attracted to another. He determined that the change in enthalpy would always be the same no matter how many steps you take. So whether you take one step, two steps, or three steps, so change in enthalpy will be same whether you take as many steps to get to the desired product. Okay. So we just showed you with this example. So I'm just going to write here. I'll just clear all the drawings here, and then I will go ahead and write the Hess law. So we have a Hess law here which states, here we have Hess law which states that the enthalpy change for the conversion of reactants to products is the same whether the conversion occurs in one step or several steps. So Hess law is very useful for studying. So you must be wondering why we are after Hess law. It is very useful in studying energy changes in chemical reactions that cannot be analyzed using calorimetry. Okay, so it finds its application for measuring enthalpy changes in the chemical reactions that cannot be used by that cannot be done using calorimetry. Some reactions, such as if you talk about reaction of glycerin with potassium permanganate, they are too fast and dangerous. Other reactions, such as synthesis of nitrogen dioxide, as we just showed you, they occur too slow. So let's show you with a figure illustration, a graphical representation maybe, to show you that the enthalpy stays the same. So if we have on this graph, on this axis, we have enthalpy, which is delta H measured in kilojoules. And then on this axis, you have your reaction progress. So what will happen? Let's talk about the two-step process, which we just showed you for nitrogen dioxide. So you have these reactants here, N2 plus O2, and it converts first to, if you give energy to the system, it will become the reactant, product, O2 plus NO. So just for the balancing purposes, I'm putting 2 here and 2 here. Okay, so I'm going to write this one again. So N2 plus 2O2. Okay, so this is your first step, and then what is the second step? So from here, it will go to, from here it will become O2 plus NO, 2NO will become 2NO, 2NO2, your product. So this is your final product here. Okay, so I'm going to write the delta H values. If you can recall, it was for the first step it was 180, and for the second step it was your negative 112. Okay, so what is the total delta H here? So delta H total, I will write a T here. So you're going to add these. Let's say this is 1, this is 2. So delta H1 plus delta H2, which is 180 plus minus 112. It's 2 here. Okay. So answer would be 68 kilojoules. Okay. And then if you go ahead and take the one step process here, so I'm going to write here the one step process. So what is going to happen here? So you have your reactants here, nitrogen plus oxygen. Let's write two oxygens. So two oxygen, this is for balancing purposes. They become the product, which is 2 nitrogen dioxide, right? So this is your one step process. And what is the delta H involved here? from going here to here, the delta H is 68 kilojoules. So this is a graphical representation of the Hess law using this one-step and two-step process for making NO2 gas. Now let's talk about some rules here, and then we'll solve some problems on this Hess law. So what are the rules here before we go to the problems, because we should know the rules. So let's write the rules here. So what's the first rule? So first rule is, I will go ahead and write it for you. So these are the rules for enthalpy changes in Hess law, right in front of you. So what you have is the first one, reversing chemical reaction. So you must reverse the sign of enthalpy value also. Okay. So for example, if this is your reaction here, xenon plus fluorine, both are gases. So you will go ahead and write gases here, G. Okay. So it will become XeF4, which is solid. And if delta H related to this equation, so for the balancing purposes, must put 2 in front of the F here. So it's 4 here and 4 here. So what is delta H value? It's, let's say, negative 251 kilojoules. And if you reverse this equation, so reverse means the products become the reactants. So when you reverse this, it will behave similarly as mathematical equation. So xenon and the reactants will be the products here, 2F2. So you must reverse the delta H value. So reverse the sign of enthalpy value. So it was negative here. When you will reverse it, it will become positive 251 kilojoules. So going from here to here, it's negative, and going from here to here, it should be positive, right? So this is what your first rule says. So you must practice this while solving the questions. And the number two, the magnitude of enthalpy is directly proportional to the number of moles of reactants and products in a reaction. If the coefficients of a balanced chemical equation are multiplied by a factor, then the value of enthalpy is multiplied by the same factor. Okay. So for example, if you have xenon plus fluorine becoming xenon fluoride. Okay, so this is a gas, this is a gas, you put 2 here, right? So let's say I multiply this whole equation by 2. So I have this first equation and I write multiply equation 1 by 2. So let's say I multiply it by 2. So what would be the result of that? So 2 xenon plus 4F2 becomes 2ZeF4. And I forgot to write here delta H value. So let's go ahead and write the delta H value here. So the delta H value, which is for the first one, is negative 251, right? It was negative 251. So this is your first equation. So let's write this is your first equation and multiply 1 by 2. So you multiply it here. So it says if you multiply the balanced chemical equation by a factor of, by any factor, which is 2 in this case, you must multiply the enthalpy value by the same factor. So this enthalpy value should be multiplied by 2 as well. So delta H will be equal to, when you multiply it, it will become 2, 0, so minus 502. Okay, so 251, if you go ahead and multiply, it should, yeah, 500, negative 502 kilojoules. So this is what these two rules are. We will see how we use them in the upcoming problems here. So let's go ahead and try to solve one problem. This is the first question on Hess law. So using the data in figure 1 and figure 2, this is your figure 1 and this is your figure 2, calculate the enthalpy change for the conversion of graphite to diamond. So carbon graphite converting to carbon diamond using this data here. So what does this data states? So this is your carbon graphite plus oxygen. It's converting into gas carbon dioxide gas here, and the delta H involved is minus 394 kilojoules. And here you have carbon diamond plus O2 becoming CO2 gas, and then the delta H involved is 396. So first is to write the balanced thermochemical equation. So what is the step one? So I will write the step one first. And let's write the balanced thermochemical equation for these combustion reaction. This is a combustion reaction. Carbon in the graphite, it is reacting with oxygen. So whenever anything reacts with oxygen, we call it combustion reaction. So let's go ahead and write that. So C graphite, I will just write G here, and then let's write Gr so that we don't confuse. And then it reacts with oxygen to form CO2. So oxygen is 2, carbon is 1 on both sides, right? Oxygens are 2 on both sides. And what is the delta H value? So when you go ahead and write the thermochemical equation from our previous lectures, so you might be knowing that we do write the delta H value, the heat enthalpy change, and that is involved in this reaction. So this is your step number one. And then we have to do the same thing for your diamond. So I will write Di plus O2, it becomes CO2. And what is the delta H? That is involved negative 396 kilojoules. So this is the first step you are going to do to write the thermochemical equation. Now, what is the second step? So the second step is to rearrange the equations as needed to get the desired um, reactant and product. So what is we have to rearrange these equations. Let's say this is your first equation, this is your second equation. So this is the data given. So you have to play with these two equations to get this equation. This is your required equation that your question is asking. So for that, we want graphite on the left hand side, that is as a reactant. So here graphite is your reactant, so we don't need to do anything with this one. However, in the desired equation, we do want carbon diamond on the product side. If you go ahead and check the second equation, the carbon diamond is on the reactant side, so you need to bring this diamond, this one over here and this one over here. So you want to make this C diamond as your product. So for that, you want to reverse the equation number 2. So I will write that over here. So reversing the equation number 2, this is step 2, reverse equation 2. Okay, so what would be the result of that? So you will have this equation, CO2 becoming C diamond plus oxygen, and delta H, as we just studied the rules, if you reverse the equation, then you have to reverse the delta H value as well. So it was negative here, it will become positive here, 396 kilojoules. So this is your equation number. Let's say I will write 2 dash. Okay, now what do we need to do? Now we need to add the equation number 1 and equation number 2 dash to get our desired equation. So if I add the first equation to the 2 dash equation, so I will have carbon graphite on the reactant side and diamond on the product side. So let's, this is our step number 3, add equation 1 and 2 dash. You can also give it the name 3 also. So I'm going to write the first equation, which is C graphite plus O2 becoming CO2, and don't forget to write the delta H value. So we didn't do nothing with this one, so it will stay as it is, which is negative 394. And this is my 2 dash equation. So it is CO2 becoming C diamond plus O2, and delta H for this one is 396 kilojoules. Okay, so let's go ahead and add it. And when you're going to add it, you already know that what will cancel here. If you see it nicely, CO2 is on the right hand side, one CO2 is on the left hand side, so you can go ahead and get rid of that. And then also you find oxygen on the left hand side and one oxygen molecule on the right hand side, so you can get rid of that as well. So what is the left over things? We can go ahead and write that. So I have C graphite on the left hand side and C diamond on the right hand side, right? So this is our desired equation which our question is asking. So we got that, and let's do the same thing to the delta H. Since we added these two equations, so we have to add these two values as well. So minus 394 plus 396 should give me 2 kilojoules of delta H. So This is the required answer. So this is your answer to this question. Let's go ahead and solve one more problem on this question. Sorry, on this topic. This is our question number 2. Calculate the enthalpy change of the following balanced chemical equation using the data given. What is the equation that we have to find the delta H for? So we want to find delta H for this equation. C2H6 gas becomes C2H4 gas plus hydrogen gas. So delta H, this is the question that is being asked. And what is the data given to calculate that? C2H6 plus 3.5O2 becomes 2CO2 plus 3 water. This is the delta H value for the first equation. This is the second equation, which is the delta H value for which is also given. And this is the third equation. This is given. Okay. Now, what do we do for this? So, first of all, let's give a look at the required equation. So we require C2H6 on the reactant side. So we do have an equation in which C2H6 exists on the reactant side. So we don't need to do anything with this equation. We can use the, let's say this is your first equation. Just one second. So we can go ahead and use this equation as it is. So let's say this is your first equation, right? Now let's write it here. Okay, now next is, if you look at the desired equation, C2H4 exists on the product side. So we do have an equation where we have C2H4. But if you look at this equation, C2H4 here exists as a reactant. So we need to reverse equation 2. So this is equation 2. And let's go ahead and write here so that we don't forget. We need to reverse equation 2. Okay. And then we want hydrogen as well in our final equation on the product side. So we do have one equation, which is equation number 3. But again here also your hydrogen exists on the left hand side, which is on the reactant side. So you need to reverse that equation as well. But if you see here, we just need one hydrogen. In the given equation, we have two hydrogens. So we need to divide this equation number 3 by 2 as well. So we need to do two operations on the third equation. Reverse and divide equation 3 by 2. So we need to reverse and then divide by equation 2. So now let's go ahead and write the result of this one. When we reverse equation 2, so what result do we have? So we have 2 CO2, 2 water on the reactant side, and C2H4 plus 3 oxygen on the product side. This is what we wanted. Okay. Now don't forget to switch or reverse your delta H value as well. It was negative here and now you're going to get it as positive. Let's write this equation as equation number 4, which we are going to use. Now, what is the outcome of this operation? Reverse the equation number 3 and divide it by 2. So let's go ahead. First, divide this equation by 2. So I'm just going to write the equation as it is. 2 hydrogen plus O2 gives you 2 water. So first, let's divide by 2. So dividing by 2 means, so you go ahead and divide by 2. Okay. So what do we have is, I will write here. So I have hydrogen plus half oxygen becomes water, right? So this is your equation. And then you need to reverse it also. Then I will write reverse. Okay. So after reversing, what do we have? Let's write it here. Water becomes hydrogen plus half oxygen. Okay, now we get hydrogen on the product side, which we want here in the final equation. So this is your equation number 5. Okay, now we have these two equations ready, and this one is already as it is we are going to use. Let's go ahead and add these equations. Equation number 1, equation number 4, and equation number 5. So I will write here, adding equation 1 4, and 5. So let's go ahead and do that quickly and let's see what we get now. Um, let's write the equations. C2H6 plus 3.5 O2 becomes 2 CO2 plus 3 water. So delta H value, don't forget that, minus 11559. We are doing everything for delta H value, so don't forget that. And then we have to add the fourth equation, which is C2H4 CO2, the same. Let me erase it more quickly. So you have 2 CO2 plus 2 water becomes C2H4 plus 3 oxygen, and delta H is 1411. And what is our last one? This is the one. Okay, so I'll just highlight these for you so that we can easily identify. This is the one equation, this is your another equation, and this is your other equation. Okay, so what's the last one? So water becomes hydrogen plus half oxygen. Delta H is, oh, I forgot to write delta H here, so I will write delta H here. Since we reversed and divided it by 2, so reversing will give me a positive number, and 572 divided by 2 will give you, just a minute. So let's put it in the calculator. We get 286 kilojoules. Okay, so these are our 3 equations ready here. Let's go ahead and add and get rid of the things we don't want, like which are being cancelled. So just one second, let's erase this line because we don't have much space to write. So we have C2H6, we don't have any other C2H6, so let's see here. Then we have 3.5, 3.5 oxygen here. Let's see here how many oxygens I have. 3 oxygens here and half oxygens here. So we can go ahead and cancel them. So they are on the opposite sides. Okay, and then let's see what about carbon dioxide. I have 2 carbon dioxide on this side and 2 carbon dioxide on this side. How many waters I have on this side? On the reactant side I have 2 here and 1 here, which makes 3 water, and I have 3 water molecules on the product sides as well. So let's go ahead and get rid of that. So let's now quickly write what is left. C2H6 is left on this side and nothing else is there. And what is left on this side? I'm left with C2H4 and plus hydrogen, right? So this is what we want. This is our desired equation: C2H6, C2H4, and then plus hydrogen, right? Now let's quickly add the delta H values as well. Let's put it in a calculator and find out. So minus 1559, 1411, and 286. So this should give you 138 kilojoules of the value. So I'm going to write some practice questions at the like now after this. So you can go ahead and check those as well, and the answers will be given. So yeah, I'll see you next time. Thank you.